So the strategies that we're going to get out of the game solving in general are not deterministic. They say, well, you know, if you're, let's look at reachability. If you're in one ring, you have to go to the next ring. There may still leave some choice on how you do this. And you have to resolve this choice. If you want to have a program or a piece of hardware, you have to say, for this state and this input, this is the next state. So you have to figure out which next state you want. And you have to do it in some way that the program that comes out is efficient. And that's difficult to do. And the main difficulty is because you have dependencies. Let's see if I have an example. So this says relation determinization. Yeah, so you may have things like this. If this is your input, then these are the allowed outputs. So with input 0, 0, I could output 0, 0 or 1, 0. With input 0, 1, I could do 0, 1 or 1, 0. With input 1, 0, I have to do 1, 0. With input 1, 1, I have to do 1, 0. So these two are easy, but this one, for instance, is a little bit more complicated. So you have to make sure that you actually pick one of these two rows and that you don't mix them up. So you cannot look at the two inputs, at the two outputs independently. And if you have a symbolic algorithm to do your computation, you'll come up with relations like this that are represented as BDs. And then you need to efficiently come up with a circuit that is a function that satisfies this relation. And this is a little bit tricky and kind of fun. But I'm not going to tell you. Small number of gates. A bunch of material in there. Okay. All right. So this is the whole story. How do you do synthesis? Well, you have to come up with a specification. You take the specification, turn it into an automaton. You have to make sure that the automaton is deterministic. And then you can play a game on it. And when you have the strategy, you have to turn the strategy into a program. And there's a little bit of stuff that I only told you on the side, so let me just make this explicit again. So the expensive stuff, we talked about this a little bit. There's two expensive steps. One, if you're doing LTL synthesis, there's two expensive steps. One is to get from LTL to Bucchi automata. You can download a tool that does it for you, and they're often very nice. But there's an exponential blow-up here. This is your first exponential blow-up. An exponential blow-up is not so bad, right? Stock solver is an exponential blow-up, who cares? But then, in general, you get a non-deterministic automaton and you have to determinize it. And this is another exponential blow-up. And this gives you a doubly exponential blow-up. And this is often too much. If you have a deterministic parity game, and I didn't show you the details, then you have to solve this deterministic parity game, but this is, I'm lying here, this is sort of polynomial. It's exponential in the index of the parity game. The index of the parity game doesn't suffer from the second blow up, so you don't. So just in case you know about this and you think I'm lying. Okay, so you get a doubly exponential worst case complexity, and that's bad. And the bad thing is you cannot do any better, so there's a lower bound result in this. Okay. Now, you can still try and do this, and if you optimize carefully along the way and you do everything very properly, then you may still be able to synthesize quite a bunch of stuff. So let me just spend one slide talking about an alternative. And the alternative suffers from the acronym GR1, Generalized Reactivity of Index 1. And this is an idea by Amir Lueli a couple of years back, 10 years ago. And there's two dirty tricks in there. So you say, what is expensive? The translation from LTL to non-deterministic Buki automata is expensive? Fine. Then why don't you specify your stuff as Buki automata? And we missed the first translation blow up. Okay, good idea. But then there's another exponential blow up from non-deterministic to deterministic automata. Okay, you don't want to suffer this blow up, then you specify your specification as a set of deterministic automata. And in this case, you don't want people to have to specify deterministic parity. Parity is hard to understand. So you ask people for sets of deterministic Buki automata, for the assumptions and for the guarantees. And if you do that, you've sort of gotten rid of both of the problems, right? Both exponential blow-ups are gone. Now, you still need to solve the games. So now this is a GR1 game, and you haven't quite learned how to do this, but it's, you know the Buki games, you've gotten pretty close. You can still use BDDs. Oh, maybe I should talk about the BDDs a little bit more. You can still use BDDs, and it's not all that much different from what we've seen. And this works relatively efficiently. So we've done implementations of that, and turns out to be efficient. And the other important thing is it turns out not to be very hard to specify realistic circuits as deterministic Buki automata. You can do it. So we did this. It's been quite a while. We did this for this AMBA arbiter. So ARM has an on-chip bus, which is called the Advanced High Performance Bus, and there's an arbiter that controls the bus. And there's a 100-page document that tells how the arbiter should work. And part of that is electric and stuff, but part of that is functional specs. So you copy these functional specs into deterministic Buki automata, and you can do that. And it's not trivial, but the Buki automata you can understand, and we've talked to people at the ARM help desk about this, and they understood what we did. So it's quite understandable. And then you can actually synthesize these systems, and that works quite well. Okay. So if you do this, so both of the exponential blow-ups are gone, you get polynomial complexity. You have to take this with a grain of salt, but yeah, that's not that. So you've seen all the details except for how to do the GR1 game. So one comment that I wanted to make along the way. Let me go back, and then I'm done. This is not easy. I just would like to connect the BDD stuff with the game solving stuff. Let's look at reachability. This section, too simple. Okay, so here you actually cannot see, so I'll go back to the pre. But you start with a set. You represent the set as a BDD. And then while this set changes, you keep computing the pre of this set. This you can do using BDDs, and the only way I can prove this to you is by showing that you can do the pre using BDDs. So we're going to go back to that. Solving worsts. So if you remember, the pre of x is x union the force of x. Now, union you can do using a BDD. This is the OR of the function. This here, the force, this, how do you implement force? Well, you take the set X, and you have a set of edges E. And you represent E also as a VDD. How does that look? So you have a set X. Okay, so first of all you have variables for your states. So you have a set of variables Q, which are all the latches in your system. And you make a copy of that, and you call it Q prime. So if you have a latch V here, here you have a latch V prime. Okay, now you have a transition relation, T, or E, and you express this as Q and Q prime. So this is a formula that talks about states that we have now and at the beginning of the edges and the states that are at the end of the edges. Now if you want to compute, let's look at the first part. So you want to compute if there is an edge to X. Then you take X, and this is also a formula. You have to make sure that this is a formula that talks about the places that the edges go to. If you take the end of this, then what you get are all the edges that end in X. And you take that, and you don't care about the end points of the edges, you care about the beginning points of the edges, right? You want to know from where can I get into X. So what you do is you existentially quantify out this existential quantifier. You existentially quantify out Q prime. And what you get is a formula, let's call it R, in terms of variables Q. So maybe this, I should have taken 2 slides to explain this. But this is the basic idea. And the for all, you can do the same thing. Or for all Q prime, if there is an edge from Q to Q prime, then Q prime is the X. So if you don't completely get this, that's fine. But you can represent the set X and the set E as formulas, and then you can compute the force function by doing a few BDD operations, and you get the force of X. So all of this is just doing BDD operations. It's very easy to implement. If you understand BDDs, then you know the fixed points that you want. And this is what we're going to do in the afternoon. But I think Anya is going to give you a little more explanation, right? Good.
But maybe we should do a break.
But we should do a break. Until 3?
Yes.
Any more questions? Good. So then let's resume at 3. Thank you.
Could you please all